Hello students, today we'll begin the next section of the first chapter, that is part B, which is measurement of length. To measure each and every physical quantity we need an instrument, right? Like if you are measuring time, we need a stopwatch or a clock. If you are measuring temperature, then we need a thermometer. And if we are measuring mass, we need beam balance or digital balance. If force or weight, you need spring balance. And if you are measuring length, you need a scale. But these instruments have their limits, right? Limits like the scale we actually use to measure length is a meter scale, that is a meter rule, the mostly used scale to measure length. But we cannot use this scale to measure every length or length of everything. Like for smaller things like width of a wire, a thin wire, you cannot measure the width of a wire by using normal meter rule. Normal meter rule has 100 divisions, each of having 1 centimeter. So what my point is that each and every instrument has their limit. So we use different instrument for measuring different physical quantity. Even for same physical quantity we use different instrument. Like for measuring length, different kinds of length. For bigger length we use an instrument. For measuring smaller length we use another instrument, right? So here comes the term least count. Each instrument has its limit of accuracy, right? So what least count is? Least count of an instrument is the smallest measurement that can be taken by using that instrument. As an example, for a meter rule, we all know that a meter rule is 1 meter long and it has 100 divisions, each of 1 centimeter, and between 1 centimeter there are also 10 more divisions which are equal to 1 millimeter. Okay, so by using regular meter rule we can measure, the minimum measurement that we can take is up to 1 millimeter. So the least count of a normal meter rule will be either 1 mm, or you can write it as 0.1 centimeter. That is the least count of normal meter rule. Or this is also the least count of the rule or a scale that you have in your geometry box. Okay, but this scale we cannot use for measuring smaller lengths or lengths more accurately. You cannot use this scale. Suppose you are asked to measure the diameter of the pen you are using. Okay, so you cannot use your normal meter rule or the normal scale that you have in a geometry box to measure that length accurately. Suppose the pen you are using, the length is coming between 1.2 centimeter and 1.3 centimeter. So you cannot take the length as 1.2 centimeter because it is coming more than 1.2 centimeter, and you cannot also write 1.3 centimeter because it is coming less than 1.3 centimeter. So you cannot use your regular scale to measure that kind of length. Here comes the use of a new type of scale that is called vernier scale, and the instrument we use to measure such lengths is known as vernier calipers. Okay, let me show you the instrument first. So this is what we call a vernier calipers. Okay, let's understand the instrument first. The instrument has two jaws. This one is fixed jaw, that is you cannot move this jaw, and this one is movable jaw. That means you can move the jaw by using these screws. By using these screws you can move the jaw. So one of them is used to move the jaw and one of the screw is used to fix the jaw at a certain point. Okay, and you can clearly see that the instrument has two type of scales. This one that I am marking right now, this one is the main scale, that is a regular centimeter scale. Each division is of 1 millimeter, each smallest division is of 1 millimeter, and this is that special type of scale that is fixed on the movable jaw, that is the vernier scale. Okay, so this is the vernier scale and this is the main scale, that is a regular scale that we use in our geometry boxes, that has a minimum division of 1 millimeter. And these are the two jaws that are the fixed jaws, and these are called inside jaws. These are called the inside jaws. So what is the function of the jaws? You can clearly from the image that whatever length that you are measuring, or whatever that has been given to you to measure the length of or to measure the diameter of, you have to fix it between these two jaws, which is being marked as J1 and J2. And then what is the function of these inside jaws? The inside jaw is used, or the inside jaws are used to measure something that is hollow, something like hollow cylindrical substance. To measure the inner diameter, we'll use this. So if this is a hollow cylinder that has been given to you to measure the diameter of, so by moving these vernier scale, by moving this movable jaw, you have to first fix the inside jaws inside the hollow cylinder, and by this method you can measure the inner diameter of that hollow cylinder. Okay, now there is also a thin rod like structure over here which is been marked as T, and whenever you're moving this movable jaw by using the screws, this will gradually come out. Whenever this section goes this direction, this rod like structure will also gradually come out, and whenever this section goes this side, this will again go inside. So what is the function of this rod like thin structure which has been marked as T? This is actually used to measure the depth of something like this kind of hollow cylindrical object, or whatever it is that has been given to you, this particular part that can be used to measure the depth. Okay, now let's learn how to use this instrument to measure the length more accurately. Okay, first we need to find out the least count of this instrument, that is the minimum value up to which this instrument can measure. Whenever you are fixing the two jaws, that is the fixed one and the movable one together, the zero mark of the main scale should coincide with the zero mark of the vernier scale. And if you closely observe, you'll find that 9 division of the main scale will be equal to the 10 division of the vernier scale. So 9 division in the main scale will be equal to the 10 division of the vernier scale. Here you can clearly see that the zero mark of the main scale is coinciding with the zero mark of the vernier scale, and 9 division in the main scale is equal to 10 division of the vernier scale. It's clearly visible here. 10 vernier division equal to 9 millimeter, right? So 10 vernier division equal to 9 millimeter. So 1 vernier division will be equal to 9 by 10 millimeter. So the difference between one vernier division and one main scale division. One main scale division, the minimum division is of the range 1 mm, and we just find out that one vernier scale division is equal to 9 by 10 mm. So the difference is 1 minus 9 by 10 mm, that is equal to 1 by 10 mm. That means using this device you can measure the minimum length up to 1 by 10 mm, that is equal to 0.1 mm. In centimeter, that will be equal to 0.01 centimeter. That is the least count of this device, that is the vernier calipers. This 1 by 10 mm is the gap between the minimum division in the vernier scale and the minimum division in the main scale. That means if you zoom the picture a little, this little gap from here, the gap between the main scale and the vernier scale, sorry, what I'm marking with red here, this little gap is of the range 1 by 10 mm, that is 0.1 mm or 0.01 centimeter. So by using these vernier calipers you can measure the length up to this range. Here you can also use the formula to measure the least count of vernier calipers. How? The least count is equal to the value of one main scale division, minus the value of one vernier scale division. The value of one main scale divisions, sorry to write in the short form, minus the value of one vernier, the vernier scale division. Okay, now the one main scale division is of the range I just calculated, that is 1 mm, and one vernier division is equal to 9 by 10 mm. So that makes the difference is 1 by 10 mm for this vernier calipers. Okay, now in the vernier scale, if the number of vernier division is n, so surely in the main scale the number of division will be n minus 1. Now if the value of one main scale division is x, then n number of division in the vernier scale will have the value n minus 1x, and for one division in the vernier scale will have the value n minus 1x divided by n. And the value of least count is, as I mentioned earlier, the least count is equal to one main scale division minus the value of one vernier scale division, that is for this particular case is this value. And I mentioned earlier that one main scale division is x, so the least count will be equal to x minus this one. Okay, and this gives me the result is equal to x divided by n. That is, so what was n? N was the total number of vernier division, and x was the main scale division. So what I showed you earlier, that can also be drawn, or that can also be calculated by using this formula. Okay, so for that vernier calipers that I showed you earlier had 10 vernier division, and in the main scale the minimum division was of 1 mm. So by putting the value you can find out easily the least count will be 1 divided by 10 mm. How will you find out the length or the diameter of the object that will be given to you. First you have to fix the object between the two jaws, that is the fixed one and the movable one, and observe the scale very carefully. First observe very carefully which mark in the main scale coincides with the zero mark or crosses the zero mark of the vernier scale. For this particular figure, you can clearly see that 1 mm, 2 mm and 3 mm. The zero mark of the vernier scale just crossed the 3 mm mark of the main scale. So the reading of the main scale will be 3 millimeter. First let's take the reading, and then you have to take the vernier reading or the vernier scale reading. And to take the vernier scale reading, you have to closely observe which mark on the vernier scale is coinciding with the main scale, which mark on the vernier scale coinciding with the main scale. For this particular figure, the sixth mark in the vernier scale is coinciding with one of the mark. It can be any mark, you don't have to find out the number from the main scale. Just look which mark from the both scale is coinciding and look at the vernier scale. Just take the vernier scale reading. From here, in the vernier scale, the sixth mark is coinciding with one of the mark in the main scale. For this particular scale, that is 1, but you don't have to look at that, just look at the vernier scale. So here, from here, the vernier reading will be 6. Now to calculate the diameter or the length of the object, just multiply the least count with the vernier reading and add it with the main scale reading. The least count was 0.1 mm, so 6 multiplied by 0.1 gives you 0.6 mm, and the main scale reading is 3 mm. So the total reading or the true reading of the object will be 3 mm plus 0.6 mm, that will be equal to 3.6 mm. And if you take the reading in centimeter or calculate the reading in centimeter, you will get 0.36 centimeter, right? So this is how you calculate the length or the diameter of the object that will be given to you. And let's see the table of finding out the length or the diameter of a given object then. So you can't calculate the diameter or length of an object by just taking one reading. Okay, you have to repeat the experiment for different positions and you have to take the mean. So this is the scale of measuring length by using vernier calipers. You can clearly see that these are the place for main scale reading. Then you have to write down the vernier scale reading here, vernier division, that is the point on the vernier scale that will coincide with the main scale. And here you have to multiply the vernier reading with the least count and write it here, and here is the total reading or the observed length, that for our case was 0.36 centimeter. Now not all the vernier calipers devices are perfect. Okay, whenever you're fixing the two jaws, that is the fixed jaw and the movable jaws together, the zero mark of the main scale should coincide with the zero mark of the vernier scale, and if not, the vernier calipers is surely faulty. So it's not a big problem. This is called a zero error. Okay, the zero mark of the vernier scale division will either cross the zero mark of the main scale division, or it will be behind the zero mark of the vernier scale division when the two jaws are together. Okay, so if the zero mark of the vernier scale division is behind the zero mark of the main scale division, this is called a positive zero error. And for another case, if the zero mark of the vernier scale division crosses the zero mark of the main scale division, this is called a negative zero error. So first let's look at the positive zero error then. This is the positive zero error. From here you can clearly see that the zero mark of the vernier scale is behind the zero mark of the main scale. So how will you find out the error then, or how will you calculate the error then? Just find out which division in the vernier scale is coinciding any of the division in the main scale. For this particular scale, 6th mark in the vernier scale is coinciding in one of the mark in the main scale. So our positive zero error will be the amount of error, that is 6 multiplied by the least count, that is 0.1 millimeter. So our value of positive zero error will be plus 0.6 mm or plus 0.06 centimeter. Now let's see the negative zero error. This is the negative zero error. You can clearly see from the picture that the zero mark of the vernier scale has crossed the zero mark of the main scale. So how will you calculate the negative zero error then? The method is almost similar. You have to find out first which division in the vernier scale is coinciding with one of the division in the main scale. From the figure it is the same, the 6th division, but to take the reading you have to subtract the value from 10. So here the vernier division is 6 and 10 minus 6 is equal to 4. So this is the actual value of the negative zero error, and just multiply it with the least count, or 0.1 millimeter or 0.01 centimeter. So the value of negative zero error will be 0.4 mm with a negative sign. Okay, now this is one method, and another method is you can count it from back side. Okay, if you count it from back side, you'll find that 1 2 3 and 4, 1 2 3 4. So the negative zero error is 4. So either you have to subtract the exact value from 10 or just count it from back. So this is how you find the positive and the negative zero error. And the next question is, how are you going to get the exact value then by using this faulty instrument? So how will you find out the correct reading then? The correct reading will be equal to, I am writing just the initials, CR stands for correct reading. Correct reading will be equal to observed reading minus zero error with sign. Zero error with sign. Okay, now if we have positive zero error, so as far I remember, our value of zero error was 0.6 millimeter, and the reading was, the observed reading was 3.6 mm. So the correct reading will be 3.6 minus the positive zero error, that is 0.6 mm, that gives you 3.0 mm, and you can also write it as 0.3 centimeter if you are taking the readings in centimeter. And let's see if the instrument has negative zero error. Now if the instrument has negative zero error, the formula will be same, just the sign will be altered for negative zero error. That means 3.6, that is the observed reading minus the because the zero error is negative here, so we'll put the negative sign, minus 0.6. the entire calculation is in mm, so this gives me the result 4.2 mm, or you can write it as 0.42 centimeter. So if you have any question, use the comment section below, and in the next video we'll learn to use the screw gauge for measuring radius or width of any object more accurately. Till then, have a good time.